Hi, so today we are going to learn torque on a rectangular current carrying loop in any magnetic field. Here you have one such kind of rectangular loop. It is carrying current I, and this rectangular coil loop is placed in this magnetic field produced due to north pole and south pole of the magnet taken. So you will observe that instead of translating from one place to another, it rotates at its initial place. And this rotational effect is called torque. So today we are to find the torque acting on this rectangular coil. So what is torque? Torque produces some rotational effect on object which is fixed along one direction, but it is not fixed along two other dimensions. Now consider one door. This is your one door, and this door is fixed along this axis of rotation. And if you apply some force, you will observe some rotational effect in this door. Door rotates through some angle. And this rotational effect is considered as torque. Now, greater the force, greater will be rotational effect. So, torque directly depends on force. Now, another thing you will notice that if you are applying some force near to axis of rotation, near to axis where the door is fixed, it does not rotate. Rotational effect is very least. Means when this distance from axis of rotation is increased, then larger rotational effect. And if force is applied near this axis of rotation, then least rotational effect. It means that torque also depends on the distance from axis of rotation. Where force is applied. Here force is applied, so this distance is called distance from axis of rotation. Now one more thing, that if angle between the direction of force and R is changed, you will find that rotational effect is changed. If angle between the two is made 0 degree or 180 degree, like in this very case, you are applying a force along the axis of rotation. Here, angle between force and R becomes equal to, R here is outward direction, F is along inward direction. So, angle is equal to 180 degree, and you will find that there is no rotation, no rotational effect is there. And you know that sine theta, sine 180 degree is equal to 0. So torque depends on all these three things. When you combine the three, and torque has symbol tau, torque is a vector quantity. So tau is equal to, the magnitude of tau is equal to RF sine theta. You can also write it as the vector product of R cross F. And when you will change this, you will find that it is equal to force applied into distance from axis of rotation. Here B is equal to distance from axis of rotation. So all these things we needed to learn once. Now we will find torque due to this current coil in magnetic field. So here I current is flowing along this direction. A current I is flowing along this direction, and length of the coil, let me take this as L. So this arm will also be equal to of L length, and breadth of the coil, let me take it as B. So this opposite arm will also be of length B only. Now you have 4 arms and you have to find torques due to all the 4 arms on all the 4 arms. So let me name the arm A, B, C, D. So force on AB arm, as we know that when any wire is placed in magnetic field, then it experiences certain force, Lorentz force. Now force on arm AB, Lorentz force, F is equal to I L cross B. You can see that length vector and magnetic field vector are at 90 degree. So L cross B will be directed. Here this is the direction of B. This is your L vector and B vector is along this direction. So L cross B goes inside the plane. Inside, therefore F, magnitude of F is equal to ILB as, okay, let me write sine 90 also, because angle between L and B is 90 degrees. So this is equal to ILB and is directed inside the plane using right hand thumb rule, or better I should say screw rule. Now force on arm CD. Force on arm CD. This is your FAB and this is your FCD is equal to, again, current is same current is flowing, length also is same and magnetic field also is same. So it comes ILB as previous, but its direction will be changed. Here you can see that B is along this direction, and now current while going all along this one, here current is returning. So length vector is along D from C. Now when we apply screw rule at this very point, joining point, we find that this field is in upward direction. Here field is in upward direction. Here field is in this direction, length vector is in this direction, and force is in upward direction. Whereas at this very point, force is along downward direction. So the two forces are in opposite direction on the two opposite arms. Now force on BC and AD. So consider a door. You can rotate a door horizontally, but you cannot rotate a door in a direction in which it is fixed. So in vertical plane, when it is fixed, it cannot be rotated. So torque on these two arms must be equal to 0. So let me check this. So force on BC arm is equal to I. Now length has changed to B cross magnetic field, and both B and capital B are in the same direction. So here angle becomes equal to 0, and therefore this force becomes equal to 0. Similarly, you will find that force on DAR is equal to 0. So 4 forces we calculated: 1 force, 2 force, 3 force and 4 force. These two forces are equal to 0. So net forces, these two which are in opposite direction, this is in upward direction, So what is net force? Net force F net is equal to FAB plus FCD, and these are equal to, if FAB you are taking plus inside direction, it is inside direction. If you take it IAB positive, or even negative, because it is in inward direction, and if you take FCD is upward direction, IAB. So net force equal to 0. Now what is torque? We learned that torque tau, it is equal to force into perpendicular distance. Any one force, not all forces, any one. And any one force is equal to IAB into perpendicular distance between the two forces. Here you can see the perpendicular distance between the two forces is the width of this rectangular wire. Width of rectangular wire. This width. Okay. So width I have taken B. Therefore torque comes equal to here you have ILB. Here ILB. Let me correct it. This is not IAB, this is your ILB. And length into breadth, this is called area. So IAB, here the torque comes equal to IAB. Now suppose if we have the rectangular coil of n turns, then total torque will be sum of all the torques due to and turns. Therefore, torque net will be equal to NIAB. So this is your torque. Here two things I would like to tell you. Here you have, when you try to write in terms of cross product, because torque is a cross product of two vectors R cross B. Torque is a cross product of two vectors. So if you try to write this torque that you have obtained in terms of cross product, so you can write Ni into A cross B. Here you know that B is a magnetic field vector. Now a new vector arises here, area vector. Area vector. So what is area vector? Area vector is a vector with magnitude equal to area of the rectangular coil. And its direction. The direction of this vector can be obtained by right hand thumb rule. If you place the right hand, if you place the curls of your finger along the direction of current in this rectangular coil here you have rectangular coil, and when you place the curls of your finger along this current carrying conductor, then thumb will point along the direction in which area vector points. So, when the curl of your fingers is along the direction of current, then thumb points in the direction of area vector, vector A. So this is about area vector. Now one more vector is there. There is a term magnetic moment. As it is current carrying lobe and it is affected by a magnetic field, means it is changed into a magnet. And the element of magnetism is given by this quantity, I into A, current into area vector, and this is called magnetic dipole moment of the coil. So one more vector is here, magnetic dipole moment, vector M, and this is equal to current in the loop into area vector, means I into vector A. If you have a coil of N turns, then magnetic dipole moment for a coil of N turns, magnetic dipole moment is equal to NIA. So a new vector arises here, and the vector has direction. M vector has direction same as direction of A. So now when the coil has plane which is not in the plane of magnetic field and it has rotated through some angle, it is ABCD coil, and in this very condition let me find first of all force. Force is equal to same I L cross B as per Lorentz law. Force is I L cross B, and you will appreciate that still in this condition the length vector and B vector are at 90 degree. So IL cross B is equal to ILB sine 90 degree, and this is same as ILB. Force is same and which is acting along downward direction. Similarly, force on CD is same ILB but in along upward direction. Now what is force on BC arm and AD arm? Here you can see that length vector is along this direction and B vector is along this direction. So if you try to find force on BC arm is equal to IBB along side AD long side AD, and similarly you will find force on DA arm and this will be equal to IBB only along side upper side, this side BC. So a force on BC is along AD and a force on AD is along BC. So these forces are equal and opposite. You can see that these forces are equal. IBB, IBB, and but they are in opposite direction. This is along AD direction and this force is along BC. So the two forces cancel each other. FBC and FDA cancel each other. Now net force. And one more thing, I had just told you previously that when any system is fixed along an axis, then it cannot rotate along that axis. So force is 0, torque also is 0. You rotate a door along horizontal direction, but door cannot be rotated along vertical direction. Along vertical direction it is fixed on an axis. So torque cannot be applied along an axis where it is fixed. So now net force of the remaining two FAB plus FCD, this also becomes equal to 0 because it is your plus ILB minus ILB and this becomes equal to 0. But there will be acting some torque. Look here. The two forces are, one force is acting along this direction downward direction and the other force is acting in upward direction on the two ends. This is your force AB, this is your force CD. The two forces are in opposite direction and the two forces are on two different points. So the force will be cancelled but torque is not cancelled. And torque is equal to any one force into perpendicular distance, this distance. This perpendicular distance, and this is called torque. So let us find torque. Now torque. Tau is equal to any one force. Any one force. Into perpendicular distance. So your force is equal to ILB. And perpendicular distance, let me find. This is your perpendicular distance. D. Here you can see that angle from this width of the coil to its downward direction is theta. So what is sine theta? Sine theta is equal to base. This base is equal to D by hypotenuse B. So therefore T comes equal to B sin theta only. So therefore here perpendicular distance D, let me write, it comes equal to your width B sin theta only. Now you can see that L into B, length into width, is area of the coil, A into B into sine theta. So you can write the torque in the term of area vector 2, I A cross B, when the angle should be, this theta should be angle between A and B. So let me check whether the angle is in between A and B or not. Initially the B was along this horizontal direction. And area vector was in perpendicular direction. Now when coil is rotated and I had taken this angle as theta. So this is a right angle triangle. This angle will be 90 minus theta. And vertically opposite angle, this angle also will be 90 minus theta. So if coil is rotated by this angle, 90 minus theta angle, then its perpendicular will also be rotated by 90 minus theta angle only. So what is total angle between area vector and magnetic field? The angle is equal to, previously it was 90 degree plus this extra angle, that is 90 minus theta. So this is your 180 degree minus theta. And we know that sine 180 degree minus theta is sine theta only. So this is the angle between vector A and vector B, or you can also say angle between magnetic moment vector and magnetic field vector, as magnetic moment and area vector are along same direction. So this is equal to your sine of the angle is equal to your sine theta. So from this equation, here the angle between A and B is sine theta only. So therefore torque is equal to IA cross B, and also it can be written in terms of magnetic moment. When you combine the two, I and A, it is equal to M cross B.